Well, thank you all for coming. It's really wonderful. It's a full house almost. So, really great. Thank you for coming. I'm going to talk, as Nat said, about mineral pigments in art and architecture and try and keep to time. 8 minutes past 6. Yeah, it's going to be really kind of a travel through the mineral paint box to see what the weird and wonderful and the normal materials that have been used in as pigments. So first of all, for those of you that don't really know what a pigment is, I'm going to really be talking about pigments in paintings and to a certain extent in architecture today. So artist pigments, we're going to call these, as opposed to, you know, hair dyes, car paint, all this sort of other uses of colour. A pigment is the colouring component of a paint. And the one property that all pigments must have, whatever their origin, animal, vegetable or mineral, is that they must be able to retain their colour when very finely ground. So these are really fine-grained materials. And they need to be solids and not soluble in water or medium. And these are the really important properties, and loads of minerals have this. But of course, pigments are not just minerals. We can get mineral pigments, we can get plant and animal-derived dyes, you know, things like sepia, indigo, madder, and we can also get synthetic compounds that replicate or are analogous to minerals, for example, or indeed organic compounds as well. So I'm kind of interested in, you know, taking these pigments into paints. So how do you make a paint? Well, you know, it's quite easy. And what you need to do is mix that pigment with a binder or a medium, binding medium really is the word for it. And, you know, if you go to an art gallery and you look at a painting on the wall, it will generally say, you know, this is an oil painting or this is a watercolour. And that medium is how paintings are classified. This is actually cadmium yellow, which is a modern 19th century synthetic pigment in oil that I'm making up here. But media are, you know, all sorts of things. They're organic compounds, typically oils, which go into oil painting, things like resins, tree resins, for example, like Arabic, which is the main component of watercolour paints. You do need some kind of glue in there. If you just painted with pigment mixed with water, your painting will all fall off the wall. So, you know, you do need something to glue those pigment grains to the substrate. So, gum Arabic from the acacia tree is used in watercolours. You can use waxes, you can use beeswax in the encaustic technique. Proteins like egg yolk, for example, egg tempera painting, and casein, which is a milk-based extract, and glues like rabbit skin glue. All of these things have been used to mix pigments into paint. So, I'm not an artist, but I'll have a good go. I came into pigments purely as a mineralogist, really, and from a geological background, and I use the techniques that we use routinely in the earth sciences and in mineralogy, crystallography, and so on and so forth, to identify materials in cultural heritage. And as Nat said, I work on ceramics and stone as well as pigments. And my go-to technique is polarized light microscopy. And, you know, there's a certain school that sees this as a rather old-fashioned technique, but I'd absolutely disagree with that. And it's fabulous for looking at pigments because you can see the colour of the phase that you're looking at down the microscope. And, you know, any spectroscopic technique or something like SEM, EDS, whatever, you know, you don't see colour. So, and this is intrinsically about human choices to use colour, and so that is really important. The other wonderful thing about polarising light microscopy is that you can see if you've got a mixture of two paints together. So, for example, yellow pigments and blue pigments mixed to make a green. And again, you'll miss that sort of effect if you're just using a spectrometer and just hitting a single grain for analysis. So for those of you that remember petrology at university or use it in anger, a polarizing light microscope is essential. We've got a normal light microscope. Well, it's not a normal light microscope. It's fitted with a polarizer and an analyzer. And you do need a pretty decent one. Those kind of little toy microscopes that you had as undergraduates are not really optically up to the job here. Pigment grains are tiny, typically smaller than 40 microns. So I'm usually working at, with 100 times objective lens, so that's 1,000 times magnification, 400 to 1,000 times magnification is essential. And I also use an oil objective as well. And one of the things about pigments is that they have very high refractive indexes, and that is, that's why they're so vibrant on canvas. But that means if you don't use an oil to flatten out that refractive index, flatten out the relief, I should say, you feel like you're looking at tiny coloured mountains. So it's kind of a slightly adapted version of polarizing light microscopy that most petrologists would use. And then, anything that is being analysed in cultural heritage, I would normally say use at least 2 techniques to confirm results. And so things like I use UV light microscopy quite a lot, but techniques like Raman spectroscopy, scanning electron microscopy, and energy dispersive X-ray analysis, and X-ray fluorescence, X-ray diffraction, etc. are of course all really useful techniques for pigment analysis. And you need a reference collection. I've just got a whole loft full of full of this. That's a small sample, about a third of my actual pigment in jars collection. Books, manuals, particularly if they tell you something about the chemistry. Cabinets full of thin sections. I've probably got about 2,000 thin sections. We call them grain dispersions, I should say, rather than thin sections. And material from all over the place. And I know there are a few pigment nerds in this audience that we're like swapping our little bags of powder. So yeah, just kind of the more you see, the more you know. So mineral pigments. Now, as I say, pigments can be biological as well as mineral and synthetic, of course. But, Geological, I've got to concentrate on mineral pigments, haven't I, really? So for those of you who remember, again, undergraduate mineralogy, these are minerals that are suitable as pigments are ones that essentially do a good streak test. So I'm seeing some nods there. For those of you who are not geologists, a streak test is one of the traditional identification techniques for identifying minerals. And it comes from assaying gold and silver when you would scratch your ore across a piece of slate and see if it leaves a colour. We tend to use unglazed porcelain tile backs these days. But any mineral that performs well as a streak test leaves a streak of colour when you scratch it against porcelain, will make a good pigment. And these tend to be the oxides, metal oxides, sulfides, carbonates, phosphates, mineral salts, essentially. On the whole, silicate minerals are not suitable as pigments, however well coloured they are, because, again, for those of you that got experience of petrology, most of them are colourless in thin section in plain polarised light. So it's the coloured minerals you want, and silicates do not have that fundamental property that I mentioned in the first slide, that they retain their colour when finely ground. So there is an exception that breaks every rule, though, which is ultramarine. And this is a normal geological thin section, of some Lapis lazuli, which is the host rock for lazurite, the blue mineral, which is a sulfur-bearing howine. It's a feldspathoid mineral. And boy, does it retain its colour when finely ground. So thin sections are typically 30 microns thick. The colourless phases here are things like diopside, carbonates, dolomite and calcite, and some micas. The opaque phases, the black phases are iron pyrite. But yeah, look at that ultramarine. And so this is how, as you would view a normal thin section, 60 times magnification. The next slide is some pigments, and we've gone up nearly an order of magnitude in magnification here, so this is 400 times. And over on the far side from me, we've got ultramarine pigment, the kind of pigment that Duccio would have been using in the Renaissance, in the early Renaissance, which is, you can see there's quite a lot of geological material in there besides these stunning blue particles of this really unusual silicate that acts as a pigment. So we've got black pyrite in there, and again, these colourless phases like diopside, calcite, so on and so forth. This is synthetic ultramarine, which was first synthesized in France in the early 19th century. Absolutely structurally, chemically analogous to mineral lazurite, but much cheaper, and also much, much finer grained. So these are both images are at 400 times, but you do really kind of need to zoom in at 1,000 times to see these really fine synthetic particles. So next slide here shows just a bit of a gallery really of various pigments under the microscope, and these include organic phases like starch. I've been told I can't stray away from the lectern. Let's see if I can get the latest. So this is a starch grain, that's potato starch. These are various synthetic phases, but we've got minerals, we've got microfossils, there's coccolith there, some realgar, mercury iodide, you name it. Any kind of, any coloured material that hits those criteria will form a pigment. So, mines. I just used this fabulous picture, which some of you probably saw this in the news a few months ago, of the church in Kiruna in northern Sweden being moved, and because they're going to expand the iron mine, and Kiruna is famous for its iron ore and also for its red ochre. And I love this image because that is what the church is built from. It's built from the waste products of this mine. And, red ochre, it's your classic barn paint or indeed church paint. And, it's one of the most ubiquitous of what we call the earth pigments. So, earth pigments. This is rather a broad term, but it's a class of mineral pigments which are earthy. They're soft, they're friable, they're crumbly. They also keep their colour when finely ground. And, artists, in art speak, these are ochres. They're also ochres geologically, but ochre, when you're talking about pigments, almost certainly always means iron ochres. Whereas an ochre to a mining geologist means any soft, friable, usually metal oxide or metal oxide hydroxide or indeed metal sulfate that occurs in the supergene portion of your vein. So that's where your metal has been weathered by the hydrosphere and the atmosphere. It's been oxidized. So, these come from gossans, which is the weathered portion of an ore deposit. They can be secondary ochres that have been, sedimentary materials. They've been eroded from a gossan and transported and redeposited in a sedimentary environment. And those include kind of red soils like terra rossas, although they haven't moved very far. And ironstones as well, which like the Carstone of Norfolk, for example, or the red chalk indeed, where, you know, you've got ochres that have been redeposited in carbonate systems or sedimentary rocks. Think of the red sandstones of the Torridonian, or, you know, the Cheshire Basin, or Exeter region. So one of the things that I did when I first started working on pigments was to try and classify ochres a little bit more helpfully and bridge these gaps between geological usage and usage by artists. And if any of you paint, been down an art shop, bought yourself some paint, you'll see that these, or at least the top three, may be familiar names to you. So I'm here dividing ochre as a pigment as an iron oxide, so that's hematite, or an iron oxide hydroxide, which is goethite, rich earth. And I'm not too bothered about its geological environment at this stage. So these range in colour from red at one end, remember, which is hematite, essentially, to yellow. But there are, of course, you know, there's about 40 different iron oxide or iron oxide hydroxide minerals, and many of them are suitable as pigments. So, you know, I've also put in here perihydrite, which is actually what's in this bucket and the background, and also sulfate minerals like jarosite, iron, sodium, and iron, potassium sulfates, make lovely yellow ochres. And then siennas, we're going to add little bits of manganese oxide gradually to these mixes. So siennas have got a small percentage of manganese oxides in, and they're more typically browner coloured material. And then umbers, which are my favourite of the earth pigments, definitely contain 5 to 20% manganese oxides. And I should say, well, actually I'll talk about umbers in the next slide, but I'll talk about umbers in the next slide. And then there are wads. This is rather an unusual name. We get these strange names in all mineralogy, you know, which have origins in medieval German, for example, and wad is one of them. And these are manganese oxide ochres, manganese ochres, and they're essentially black earth. Nightmare to paint with. So umber I just love, actually. And of course, umber ochres, as I've just described them, and indeed siennas, are ubiquitous on the Earth's surface, which is why they were the first pigments used in antiquity. Think, you know, cave paintings, that sort of thing. But umbers are really unique geological rocks, true umbers. And this is some from Mica. Used to go on the Cyprus undergraduate field trip when I was in UCL Earth Sciences, and we used to always go to the Umber pit to learn about mid-ocean ridges, actually, not to learn about artist pigments. And my colleague, who shall be nameless, always used to tell us that, you know, this is where Leonardo got his pigments to paint the ceiling of the Sistine Chapel. And if you know, you know. He didn't paint the ceiling of the Sistine Chapel. That was Michelangelo. Anyway. But the students would all write that down in their notebooks, and I would be there rolling my eyes and collecting it. And the other thing we always used to do, and I did think twice about putting a photo of this in, very bizarre rock, Umber, was a competition to see who could stick the largest piece of umber on their tongues. And the winner was just, you know, it was a piece like this. It's really lightweight rock, and it's really, there's a word for it, I don't know what it is, hygroscopic or something like that, where it just kind of absorbs water, and it's really sticky when it's wet, and it's used as a drying agent in oil paint. So you can paint with this as a pigment, but you can also mix it into your oil, and it makes your oil painting dry quicker. So this is some umber pigment that I've prepared from the Cypriot umber, the best umber in the world, and some swatches up top there of the raw umber, and you know, and you can modify earth pigments by heating them as well, which I do in my cooker at home. You know, Don't try this at home, but, you know, just because I do it doesn't mean you should. But yeah, you know, you get these really, the colour hasn't really reproduced, but these really lovely conker red, chestnut brown kind of colours. So it's a really unusual pigment. And here are just some field photos on your left. Just a close-up of some of this sequence. We've got pillow basalts from the Trudar-Sophiolite on Cyprus, overlaying, well, we've got sulfide ores right at the bottom, and then we've got pillow basalts, lavas, and then these umbers are on top of them, and they're deposited from minerals precipitating out of seawater, which originated in black smoker environments in the mid-ocean ridge axis. So they're typically deposited in a kind of half-graben situation off-axis from the mid-ocean ridge. And yeah, here we've got massive sulfides again at the bottom of this pit. Again, the same sequence, pillar lavas and the brown umbers overhead. So when I took the students to this mine, Scuriatissa, to learn about ophiolites, they're all coloured in their field sketches with bits of ochre and umber that they picked up in the pits, which I thought was very nice. Green, always a problematic mineral to get hold of because there aren't many readily available ones. Green earth. And this can be either the clay minerals, iron-bearing clay minerals, glauconite, or celadonite. And we've got a cross-section, thin section at the top left of the green sand, so-called because it has glauconite clay minerals in it, Cretaceous sands of southeast England. And that's glauconite, which geologically only forms in a marine environment. But an almost identical clay mineral called celadonite forms from the weathering of basalt. And this is another pigment mineral. Cyprus really is the country of pigments, actually. And this, you know, this was sourced in Cyprus. And this I've got in my hand there, the bottom right, are some chunks of just incredibly green celadonite in the Winsor & Newton Paint Company's archive collection. And again, this is what it looks like when ground and painted up. Really beautiful colour. So, you know, landscape painting wasn't really a thing until, you know, the last 300 years or so. And you can see why, really, because you didn't have any greens to paint with. But green earth, sorry, was used as an underpaint. And here is a famous painting in the National Gallery, the Manchester Madonna, so-called, because she came from Manchester. And it's, as you can see, it's unfinished. And, you know, I love paintings that are unfinished because you really see that artist's technique. And you can see that Michelangelo has roughed out the figures on the far left in green. And he's then painted the figures on the far right in white flesh tones. And, you know, if you're going to, and I bet you remember this from primary school, you draw a picture of your dad or something, and you colour him in pink, and he looks really pink. And it's not white flesh tone. But if you're a bit like me, and after a couple of glasses of wine, you get a bit flushed, ladies in the audience may be aware, and indeed some gentlemen, that you can buy green face powder to make you look normal again. That green face powder is green earth, and Michelangelo and other painters were using that in exactly the same way. It gives you a more human skin tone. Now, often these skin tones were painted on using fugitive dye-based pigments like carmine. And that's what happened to this poor chap on the right. You know, for eternity, he's probably there lying in his grave going, why did I wear that red hat? And I do have the artist, I couldn't find it last minute, sorry, but it's in the Altes Pinakothek in Munich on display. And again, yeah, he's not green because the artist painted him green. It's green because of this green earth and the carnation, the flesh tones on top. My favourite ochres, actually, well, Umber is kind of my favourite. Joint favourite is Vivianite. And I'm very grateful for Tim Holt-Wilson, who sent me these images of Vivianite formation in a quarry, Pentley Quarry, which is now unfortunately flooded, which is shows late Devonsian, so just after the last glaciation, peats and gravels and sands. But this is the peat layer, and I hope you can see this blue encrusting material on the surface. And Vivianite is an iron phosphate mineral, sometimes called a blue ochre. I've never actually seen it in outcrop, so I was absolutely devastated when Tim said, I was like, oh, you must take me to this quarry. And he's like, oh, they flooded it, but I've got some. And he sent me more pictures. So this is a hand specimen. It's about a fist-size chunk of the peat, and you can see bits of plant material in it. And this blue, amazing iron phosphate crystallizing out on the surface. You know, so when you kind of expose the section, you see nothing, and it reacts with the light to form this blue mineral. And this is some Vivianite from Papua New Guinea, of all places, in thin section in the background. Again, a very distinctive mineral. I mean, you can't really do optical properties on this, but it has fantastic pleochroism. And these minerals were really important in Pacific Northwest cultures. And my colleague Melanie Anchetta, who's at Museum of Anthropology in the Smithsonian in North America, has done a lot of work on Vivianite pigments in Pacific Northwest culture, and she is a Native American as well. This is a so-called house dish. This is about the size of a canoe. So this is like a big trough, and you'd have filled it up with your food, and you'd have all had a big feast. So when it says house dish, I bet you can think it's about this big. It's not. It's over a metre long, and it's painted in blue and green Vivianite. And I went to an academic conference a few years ago, a long time ago now, in Alaska, in Anchorage, and I went to the local museum, which had an exhibition on about the lives of Pacific Northwest Native Americans. And there was a really great story there, which I'm going to tell you. And it was an old chap, and he recalled going with his grandfather out in the canoe to a place called Nelson Island, and his grandfather would be in one canoe and he as a little boy would have been in another, and there were these big cliffs with peats on the top with Vivianite forming them, and his grandfather would take his rifle and shoot it off the top of the cliff, and it was his job to paddle like mad and catch the bits that were coming off. So a really difficult pigment foraging expedition. But yeah, really, really lovely pigment. And, the most famous blue pigment, of course, is ultramarine, which I've already mentioned, so I won't dwell on here. Reduced from the rock, Lapis lazuli, but you're extracting the blue mineral lazurite, sulfur-bearing howine, as I said, from that. Very limited, so, it's locally abundant, but globally rare. So very limited outcrops. The most famous one is Afghanistan, and almost certainly this was the only site used in antiquity and historically. And then, in the 20th century, some of the sites have come to light in the Pamirs, in the Baikal region of Siberia, and also in Chile. And all of them have been used for making ultramarine pigments, but the Afghan stuff is the best, absolutely. It's the most intense blue. And this really only first was used as a pigment from about the 6th century Common Era onwards. Didn't really reach Western Europe until about the 12th century, but then we start getting paintings like this. And it's always associated with the Virgin Mary. This is the Wilton diptych in the National Gallery. And I really, if you don't go to art galleries very often, you should. And go and have a look at these paintings, and they're just stunning. This is English. We have very, very little English art pre-Reformation because of Henry VIII. And, so it's just astonishing, the skill here. But, we've got the Virgin and her attendants. But do you notice, this is Richard III, whose symbol was the white heart. You notice how all her attendants are wearing a white heart because they're alleged, so they're mates of the Virgin, and they're also big fans of Richard, you know. So, but you know, look at that ultramarine, absolutely beautiful, and the Virgin has the bluest of the blue robes. But you can get blues and greens from azurite and malachite. I mean, these are not particularly abundant. They, you know, ultramarine famously was, you know, worth its weight in gold, literally, or more than gold in the Renaissance. And, you know, azurite and malachite were also expensive pigments. These are copper ores, supergene copper ores, and they're basic copper carbonates, so copper carbonate hydroxides, and you know, they just make fantastic pigments. You've got to be really careful you don't grind these too small though, because they do start to lose their colour. So malachite and azurite pigments are usually quite gritty, but these are just some examples that I've made from smashing up pure azurite, pure malachite and malachite azurite mixtures. Just gorgeous colours. And just some pictures of these under the microscope. They're carbonates. Very, very high birefringence in plain polarized light, azurite, under cross polars, and malachite, and again under cross polars. So very easy to differentiate from lazurite, ultramarine, which is isotropic because it's a cubic mineral, so it doesn't transmit light under plain polarized light. I think probably one of the most famous uses of magnetite is the Scroveni Chapel in Padua by Giotto. And, you know, and it was assumed, and I must admit, I've been there, it's like, that's Lapis lazuli. For analysis, I haven't done any analysis on this, but they have come out as azurite. I'm convinced there's lapis in there as well, absolutely convinced, but there is a lot of lazurite. And, you know, these pigments have been around since, you know, antiquity. Look at his little face. This is a so-called late period, which is about the 6th century, so early Iron Age in Egypt. Coffin, when there was a trend for these green faces, because green symbolised the afterlife in ancient Egypt. And so, you know, if you've got a green face, you come back. And indeed, look at him, here he is, in the Joel sock. You know, 2,500 years later, he made it. So, yeah, and he's all painted up with malachite. And then lots of other copper salts, you know, art historically, these tend to be called salt greens. They include the mineral formerly known as chrysocolla, which was always, you know, if you go to the old mineralogy books, it'll tell you it's a copper silicate. It's probably a mineraloid, and actually the blue coloration is a mineral called spertiniite, which is a copper hydroxide. Brockentite, copper sulfate, hydrate, atacamite, copper chloride, hydrate, and you know this kind of lump of sort of random copper minerals that I've got here, you know, it could have all sorts in them, but you know, crush it, you're going to get a decent pigment. This is Vivianite, which is a copper zinc phosphate, and it's and also hemimorphite, which is zinc silicate. Vivianite is the blue, and the zinc is the more greeny. The hemimorphite is the more green. And I've just included this because it's one of the most recent minerals to be identified in pigments, and it was used in certain areas of the Atacama Desert in the Mayan classical period, you know, so which creates for about the 14th, 15th century Common Era. So yeah, we still find bizarre minerals as pigments. And yeah, atacamite is copper chloride, which you can also make very easily with some nice copper nails and a bit of salt. And in a similar way, I'm just going to give a mention to verdigris, which was the cheap source of green. I've always got a pot of this on the go. And these are copper etching plates that have been submerged in vinegar and just left to stew over a period of about 6 months. And so, you know, sequentially, from left to right. That's about, you know, day 1, week 3, month 3, 6 months, and you can see this just corroding away. And again, do not do this at home, but then you scrape it off, make it into a pigment. It's poisonous. On the subject of poisonous pigments, some of the most famous pigments are poisonous. This is cinnabar, and just an astonishing shade of red, and again, an incredibly valuable pigment. We see it in the Villa of the Mysteries, 1st century Common Era at Pompeii, and you know, these bright reds. This is a great painting, the Ladies of the Cholmondeley family. It's in the Tate. They were born on the same day, gave birth on the same day, and died on the same day. It's written on the painting, so it's a fact. And they think this actually might be a mortuary painting, you know, that it was after they had died. But there you go. We don't know if they were sisters, but they look like it, don't they? They are certainly related. And then the arsenic sulfides, it gets worse, even more poisonous. Again, you know, teaching geology did take me to some interesting places. So field trip to the Campanian volcanic field. This is Campi Flegrei in the Bay of Naples. And these are fumaroles, active fumaroles. And you can see these little cairns of rock that have been built up around them. And I had a chat with some of the, I was going to say wardens, but they were just old blokes sitting on deck chairs, having a smoke, breathing this in all day long. And I was like, so what's with the yellow rocks then? And they said, oh, we just leave them there. After about a week, they go bright yellow, and we give them to kids. And I said, can I have one? And he said, €10. So I bought it, and there it is, yeah. And yeah, this is basically arsenic and realgar ready to go. And you see these minerals in the wall paintings at Pompeii. And, you know, they were some of the best, you know, yellow ochre's great, but it doesn't really zing. We see it in Egyptian tomb painting. My former employee, the Trinity College Dublin, houses the Book of Kells, and the yellows in that, stunning colours are ornament. This is painting by Lorenzo Lotti. This Renaissance woman in this incredible dress, which is painted in verdigris and orange realgar. And yeah, just a few pictures of these. You can tell why I like looking at them under the microscope, can't you? They're much better than quartz. They really are. And yeah, just throwing this in as probably the most bizarre use of a mineral pigment. Super rare variety of fluorite called antizonite, very similar to the Blue John fluorite that we get in Derbyshire. Found in a few mines in a very small area of Bavaria, but pretty much used by every painter, who were probably only about 5 painters who lived in that area in the early 16th century. And, you know, God, you don't want to spend a night with him, do you? And then manganese blacks, these are wads that I mentioned. And, you know, bizarrely, now as a field geologist, I would struggle to find you a wad deposit, to be honest. And I'm a pretty good field geologist. But somehow, back in the Paleolithic, they were on it, and they used it, along with soot, of course, which is the main black used in painting, for painting some of these caves in France. And I use UV light for looking at hydrocarbon compounds, because you often get fluorescent phases, and you often get these kind of comet trails, as I call them, which I hope you can see, these kind of streaks that they leave behind them in the mountain media. And, you know, these became really popular pigments in the 18th and early 19th century, till they realised, because they're just horrible and sticky. People like Joshua Reynolds, whose sculpture is right next door to us, he made all his own pigments out of God knows what. And I tell you, the worst nightmare of a painting conservator is when somebody says, can you have a look at this Reynolds for me? What are they? But they use things like hydrocarbons. Now, this picture, Go With the Baby, by William Beechey, is in the Dulwich Picture Gallery, and it's consistently voted one of the most popular paintings in that art gallery. And people love its kind of slightly impressionistic look. It's a bit smeary. The reason it's a bit smeary is because it's all going south because of these oils. You know, this is not the painting that Beachy posted. And I don't know if you can see, but again, this one, again in Dutch, also by Beachy, big fan of bitumen. You can see the craquelure, the cracking on his coat. You know, not good. Coals, surprisingly, weren't used that much. These are bitumen-based pigments. But, you know, we have a nice coal vein at Bideford on the North Devon coast, which has produced very nice black pigments, not too oily. And then there is what the French call pierre noire véritable, the real black stone. What geologists call ampelite. It's not the sort of thing you come across very often. These are metamorphic carbon deposits. Presumably they were something above an anthracite in coal classification. Also shungite, very similar rock from the Shunga Peninsula in Karelia in Russia. But yeah, here was a picture of some pierre noire véritable, and it comes from the Ile de Creusot in Brittany. Some of it under the microscope. And, you know, these were used as kind of black chalks by artists like Van Gogh and the Impressionists. They became very popular then. Fossil sepia, I kid you not. These are fossilized melanin ink sacs from the British Jurassic. And, you know, you can still get these today, probably from China. But the artist who I'm a contemporary artist who I'm a big fan of, Matthew Lintock, does these beautiful prints of mountains, and he uses fossil sepia ink on them. And this is Elizabeth Philpott was hanging around, you know, in the 1830s in Lyme Regis with everybody. And this is in the Oxford University Museum. And if you can't read it, it says a jaw of the Ichthyosaurus communis from the Lias, Lyme Regis, drawn with colours purchased from the fossil sepia contemporary with the Ichthyosaurus. So that's proper art and science, isn't it? Mineral whites, chalk, so calcite, dolomite, and also kaolinite and diatomite have been used as white pigments. I'm speeding up a little bit here because I know I'm running out of time. But yeah, chalk, really great because it's got coccoliths in it, so you can tell where it's come from. You get a micropaleontologist on it, and it's like, yeah, this Rubens painting has chalk that comes from here. You know, it's really, really great. There's also a really bizarre variety of dolomite called huntite. One of the problems with chalk is it's a really transparent pigment, so it's not good for opaque whites. Lead white, which is a synthetic pigment, was the one that was mainly used for opaque whites. Of course, it's very poisonous. Huntite, we mainly see in Egyptian painting. This is a Book of the Dead that I worked on in the Fitzwilliam Museum, and this dog here is painted in this huntite with more transparent whites in its underbelly. Gold and silver. Possibly not pigments in the technical way, you know, you can apply it as leaf, but you can also rub bits of your leftover gold leaf with your finger in a shell and make a fine gold pigment. It's called shell gold. But yeah, I mean, gold leaf, sienna, 13th century, just incredible. And really nice fictive marbles on these paintings as well. And this, I think, is arguably one of the greatest paintings ever made. This is Joseph Wright of Derby's experiment with an air pump. We have this kind of mad scientist here, and he's got a bird that is on its last legs, and he's got his finger over the valve. Will he remove it and let the bird come back to life, or will it die? A lot of tension here, and the little girls are horrified by this, rightly so. But we've got this vessel full of water, and I'll zoom in on that as a detail. You can just about see on the right-hand side the reflection of the candle that is being lit. Back in the day, before we had electric microscopes, you'd have a bulb full of water with a candle behind it or a light behind it to illuminate your microscope stage. And it's only, again, only recently been found out that Joseph Wright, who was an incredible technical painter, used layers of silver leaf in this. So you would use layers of lead white, silver leaf, and something on top. And now you know that, you cannot unsee it. You know, this luminosity is just incredible. And, you know, he's a master of chiaroscuro. Yeah, just incredible paintings. And his, again, you know, gold leaf's been around as long as we've been around, really. This is a footcase of an Egyptian mummy, Roman period Egyptian mummy, 1st century BCE. And you can, gold is opaque to X-rays. You can see it here on this scanning electron microscope image. And a cross-section there. Very common to lay gold leaf on top of red ochre because it really brings out the colour. We're getting close to the end. Mica paints, thought I'd put them in because, yeah, these are often called magic pigments if you go and buy them, and you get this colour shift effect. If any of you are wearing sparkly eyeshadow tonight, you've got synthetic micas probably on your eyes. They're used as cosmetics, used for car paints, which I said I wasn't going to talk about, but... And they were used on Christmas cards. You can see this, you know, inexpertly applied mica to this jolly image of a scowling Father Christmas bringing drums and trumpets to ruin your Christmas day. But yeah, this is mica, yeah? And then, you know, we do use minerals to modify other materials. So dyes are not pigments because they're liquids, they're soluble in water. And right at the beginning I said it's got to be solid and insoluble in water. How you make a dye into a solid material is you react it with alum, which is the mineral alunite, potassium, aluminium sulfate hydrate. You can find this in places like Egypt, Western desert, many desert regions, various parts of Turkey and so on and so forth. And I'm not going to go through this, but basically the reaction is you use alum, an alkali like sodium carbonate, potassium carbonate, dissolved in water, and it will precipitate out as aluminium hydroxide. And that aluminium hydroxide pulls the dye molecule down with it, and you get a coloured material. And so this is madder lake, used in ancient Egypt again, well, it's Roman period Egypt, and in thin section on the side, and this is a dye as part of these aluminium hydroxide compounds. It's called a lake pigment. You can also precipitate lake pigments onto chalk as well, and this is Globigerina benthic foraminiferas in the base of a yellow pigment. This is a late reaction going on, very bubbly, gives off a lot of carbon dioxide. You can also use Copperas, which is derived from iron pyrites. This is the beach at Walton on the Naze. And, you know, you've got all these pyritized twigs weathering out of the London clay, and these were scooped up in the 18th and 19th century and made into this material called Copperas, which is iron sulfate, or iron sulfate hydrate. And this is a green material. You can buy it down your garden centre today. But this was used as a render architecturally. This is some Geiting Cotswold stone, inferior rhyolite, painted up with Copperas. That's what they did at Blenheim Palace, because they used a real mixture of different building stones at Blenheim to make them all look the same, slathered them all over with Copperas to make it look bright orange. And of course, it is the main component of making iron gall ink. So, you know, if you soak oak galls in water, you'll get a brown dye, like you have here on the left-hand side. You add Copperas to it, and it goes jet black. And this was the most important writing ink in the West until the 1920s, when the biro was invented. And we've totally forgotten about Copperas today. Really important. And again, finally, just something on synthetic pigments as mineral analogues. Can still use microscopy and the same techniques we use in geology to identify synthetic pigments, because the inorganic ones are very similar, are usually mineral analogues, so you know. Cobalt blue is a cobalt spinel, very rare in nature. This is an outcrop on Baffin Island. Discovered twice. It was discovered in the New Kingdom, where it was synthesized from making, from calcining cobaltiferous alums. It's cobalt aluminium oxide. And then it was rediscovered by Joseph Leitner in 1775 and reintroduced to painting. And this chemical revolution of the 18th century gives us all these new pigments, many of which, the chrome colours, cadmium colours, cobalt colours, are synthetic analogues of naturally occurring minerals. And it was really transformative because we go from a mineral-based palette with a bit of Madder Lake as the pink. It's, again, a stunning painting by Titian. But we've got ultramarine, we've got vermilion, we've got verdigris, we've got ochres, to the kind of paintings that were painted in the early 20th century, like André Derain's The Pool of London, where you've got these astonishing bright colours. And that is my final slide. Thank you all for listening.
Not overrun at all. People were really into the poisons as soon as you started talking about those, and there's lots of questions online as well. So we'll start with a question in the room. We've got a hand up at the back. There's a mic coming to you, sir, and then we'll go to a couple of online questions to Ruth.
Very interesting talk. My question was that in watercolour painting, we have two main greens, viridian and sap green, but we don't use them. In fact, we always mix our own greens from blues and yellows.
Yeah.
So why does that work?
Well, I was going to ask you that. I'm not a painter, so...
I am a geologist,
yes.
But I don't know the answer.
I don't know the answer to that. I mean, viridian's a nice green. You know, I think you can actually to answer that question.
You can get a much broader range of shades of green by mixing rather than using the standard mineral-based pigments.
And that is the truth. I mean, in Roman painting, a lot of greens you see are mixtures of a synthetic compound called Egyptian blue, which is synthetic cucurbite mixed with orpiment, gives you a beautiful green.
And my other comment is that there is a book called Colour by a lady called Virginia Finley.
Yes.
Would you recommend it to the audience? Because it's a fantastic book.
Okay, we're going to take one online. Alicia's going to read one out from the back.
Go for it, Alicia.
So, since everyone enjoyed poison, Sarah has asked, which is the most poisonous pigment of all?
Well, I think the arsenic sulfides, actually. There was a great writer of a painting manual called Cennini in the Renaissance in Italy. And he writes, he's got a chapter in his book, which is a manual on painting, and he writes about mineral pigments, and he says the very best yellow you can possibly get is orpiment. And the mineral name comes from golden pigment, or orpimento. And he said, it's the best colour you can get, but don't use it, because you will die. So, it is. It probably is quite nasty. But actually, any pigments with heavy metals in, like arsenic, cobalt, whatever, these will collect on your lungs if you breathe enough of it in. So you've got to be careful handling these. And mercury sulfides is not good either. There was a German pop artist called Zygmunt Polka, and he painted a huge painting called Goldklumpen, meaning lump of gold, and it's about 3 meters by 2 meters painting, and it's a big lump of gold on a green background, and he used arsenic sulfide, orpiment for the gold, and green arsenic, copper arsenite on the background. And the reason he did it was because he wanted to make the biggest poisonous painting ever. And our friend Anthony Malinowski has now beaten him by painting the whole back wall of the Royal Court Theatre with vermilion, the cinnabar. So, yeah, there you go. But yeah, don't lick paintings.
We're going to take another one from online first, and then we'll take one more from in the room. And Ruth, I'm just going to ask you to stay near the microphone so people online can
Yeah,
hear
I
you.
know. I'm sorry. Sorry.
Alicia, over to you.
Can you please place the geographic location... let me start again. Apologies. Can you place the geographic location of other minerals on paintings, for example, to track trade of pigment?
To track the trade of pigment, well, some things, yes. A lot of things, no. You know, there are no decent isotopes in iron oxides, for example. So very, very, very difficult to provenance. Sometimes if you get other trace elements or microfossils, you can use that. But yeah, actually provenancing these minerals is really difficult, unless it's ultramarine, you know where it comes from. So yeah, I mean, one of the things that I do is try and, you know, map out areas where certain minerals are found, like cinnabar, like orpiment, and, you know, see if we can relate these to local painting traditions. But it's very much guesstimates rather than secure provenance. Lead pigments we can do with lead isotopes, but you know it usually costs more than most art conservators are prepared to spend on restoring a painting.
Okay, I think we had a question in the middle on the edge here. Just wait for the microphone.
I'm sorry. Can you tell me why my Chrysocolla paint, when I make it, turns green after a little while? Because no one at my school can tell me why.
It's probably reacting with your medium. That happens a lot with copper salts.
Just gum Arabic.
Yeah. Yeah.
Really?
Yeah, yeah.
So
I mean, verdigris, when you make verdigris, I mean, you know, you get these blue crystals, but when you see it on paintings, think Holbein's Ambassadors or, you know, the leaves in the back of that Titian painting, it's green. And actually, verdigris is a rule breaker because it dissolves and reacts with the medium.
I don't know enough about minerals to know that verdigris and Chrysocolla are the same thing.
No, they're not.
Oh, okay.
But it's a feature of some of these copper salts that they will react
Yeah,
with the
so
medium.
I'm not seeing my azurite change that night or my malachite changing, but the Chrysocolla like goes
They are
glossy.
much more stable compounds, malachite and azurite. But some of these dodgy salt greens, yeah, they will react. Yeah.
All right, thanks so much. That was awesome.
Okay, we're just going to go back to online. Those of you in the room, we do have a drinks reception afterwards, and Ruth is very happy to answer questions with a glass of something next door. So we're just going to prioritise the people online. I'm sorry, because we have got more than 300 people online. So Alicia, back to you.
For the azurites and malachites, why does grinding the rocks too fine cause loss of colour?
You know, I don't actually know, but it's a true fact. And one of the things that you get used to when you're making paints, grinding malachite, is that I've learned when to stop. You see the colour change and you've got to stop. And I think it's probably down to, well, colour in malachite is promoted by the copper. So yeah, you know, I'm kind of dredging at my scant mineral physics knowledge here. It's, you know, so colour in silicate minerals, for example, some blue kyanite up there, that's formed by colour centres, which are defects within the crystal, and if you grind something too small, you lose those defects and it loses its colour. That's not the case with malachite and azurite. I'm going to have to draw a blank on that one. I don't know why it happens, but it does.
Great answer.
Ask a physicist. Always my answer to these questions.
And Lucy has asked, could you let us know what projects you're working on now or any recent highlights?
I'm writing a book on pigments, which hopefully will be out next year, all being well. So that's mainly what I'm doing at the moment. I'm also doing quite a lot of work on Copperas at Blenheim Palace and how it's been used historically. Yeah, and just messing around, really, making stuff and having a go. And I should also say, you know, one of the things that has really pushed my knowledge of these materials forwards is working with contemporary artists. So, you know, big thanks to Joe Volley, who is a fellow pigment nerd who's in the audience here, Sarah and Rob and Anya McCausland, you know, and just actually seeing how artists use these materials rather than just looking at them as a scientist, you know, how they paint up, what, you know, what you just said about these reactions that you don't expect, this knowledge is really, really useful and makes me think more about the physics and chemistry of these minerals.
Okay, well, I think that is a wonderful place to finish the formal part of the evening on. So please join me in giving Ruth another round of applause.
Thank you, everyone.